All right, welcome to lesson 8.04. This is the last lesson of this mini unit where we've been integrating calculators into our work with integration. Here we're going to look at AP free response problems that deal with function characteristics. So unlike the previous two situations, which are both real life situations in context, these are sans context. So just dealing with a function abstractly. Plus there are going to be some extra practice problems that are from previous AP tests. So this should be mostly you actually doing work and very little of me actually talking. Before we get started, I want to hammer home once more the most important, simple, and powerful fact that we have learned thus far, the fundamental theorem of calculus. Here, u is a function of x, and if I'm taking the derivative with respect to x of the integral from a to u of g of t dt, remember, this here is the antiderivative. So when I take the derivative of the antiderivative, pretty simple. G evaluated at u times the derivative of u with respect to x. Things that are commonly missed here are that we need to make sure we're using the chain rule here. If u is a function of x, we cannot forget to take the derivative of u with respect to x. Secondly, we have the simple fact that the integral from a to b of f prime of x dx, this is simply the change of f, not f prime, the change of f between a and b. In other words, it is f of b minus f of a. You can think of this as literally what we mean when we say displacement. When we take the integral from a to b of the velocity, that is simply the change in position between a and b. And so this leads us to a really nice fact, which is, look, if you're trying to find the value of some function at some value, let's just call it b, then you can find that if you know simply the value of f at any value a. Because if we solve for f of b, we get this. All I've done is add f of a to both sides. So think about what I would need to know to find the value of function f at any point b. I need to know the value of the function at some point a, and I need to be able to take the integral from a to this point b of the rate of change, right? You can think of this as simply being the displacement of my function f between a and b, right? This is exactly what we've seen with position and velocity. And so in general, we can find the value of any function at some point t if we simply know an initial condition, the value of the function at some point a, and we have the derivative of f, which we can then integrate from a to t as such. I really can't overstate how powerful this is. This is allowing us to find the value of some function at any point t. So long as I know the value of the function at some point a, and then I have the derivative of that function, then I can take the integral from a to that point t. So with both these facts, you will be well prepared, so long as you deeply understand them and can implement them when necessary. All right, let's go ahead and take a look now at a functional analysis free response question. All right, so let's take a look here at a problem from 2006. You can use your calculator here. Go ahead and copy the question down. Make sure you have the graph as well. And then give yourself 15 minutes, see how far you can get. And once you know to where you got after 15 minutes, take however long it is necessary for you to finish all of the problem. And then we'll take a look at it together. So to start off with, there are a couple of key points that I need to make sure I remember. This function f is defined for x greater than or equal to 0. I know the value of f at 0 is 5. I'm given the first derivative, f prime. I'm given its algebraic form, and I'm given the graph of f prime. F prime. I'm not given the graph of f. That is super important to note. All right, let's take a look at A first. Use the graph of f prime to determine whether the graph of f is concave up, concave down, or neither on the interval between 1.7 and 1.9. So I've annotated here approximately 1.7 to 1.9 on my graph of f prime. And I need to ask myself now, if I want to make a conclusion about f and its concavity, what is it that I need to analyze? And I need to analyze the value of f double prime. So in order to determine concavity, I am going to ask myself, what is f double prime of x on this interval? Well, f double prime is the derivative with respect to x of f prime of x. And so to evaluate this, I need to think to myself, what is the rate of change of f prime on this interval? Well, f prime is clearly decreasing, so that means its rate of change will be negative. So this is negative, which tells me that the second derivative of f is less than 0, and therefore the concavity is concave down. So here's my answer written out. Since f prime is decreasing, f double prime is negative, exactly what I showed here, and thus f is concave down on the interval from 1.7 to 1.9. All right, part B says on the interval from 0 to 3, the closed interval, find the value of x at which f has an absolute maximum, justify your answer. So notice here I'm on a closed interval, so I can apply the closed interval test, and I can also note, since I am looking at this graph, it's pretty easy, and this is f prime, right? I can see here that the value of f is going to be increasing, then it's going to go decreasing, and then it's going to increase again. So on my closed interval, the only points that I need to consider for an absolute maximum are the points at which the function is going from increasing to decreasing. So in other words, I really just need to evaluate the endpoint here, and where is it going from increasing to decreasing? Right here. So those are the only values that I actually need to evaluate, and I'll make that clear in my solution. Well, what is this value here? This is going to be the value at which f prime is equal to 0. So I need to solve for that. Okay, so setting f prime equal to 0, the quickest, I think, way to do this whenever you're presented with a problem in which you have your calculator is to take your function, f prime, graph it, and use your calculator to find that root here. Okay? But we should know, you can do this by hand pretty quickly, and you should know how to do this. If you set this equal to 0, e to anything is never going to be 0. So our only option is when sine of x squared equals 0. And we can think about that pretty quickly. If you just envision your unit circle here, sine is going to be equal to 0 when the argument, in other words, x squared, when x squared is equal to 0, which means when x is 0. Or when x squared is equal to pi, which means x would be square root of pi. Or continuing around, when x squared is equal to 2 pi, meaning x would be the square root of 2 pi. And when x squared is 3 pi, and so on and so forth. And we know we're looking for the first root, so here's when x is equal to 0, and this will be when x is equal to the square root of pi. So we get 0, and then we get square root of pi, and then we're going to get square root of 2 pi, so on and so forth. And you, of course, know that the one that you care about is this first root here, and so you want to find the value of this. So if you didn't go the by hand method and use your calculator, remember we don't care about this one, square root of pi is approximately equal to 1.772. So now I have my critical point at which my derivative changes from positive to negative. I'm going to test the two endpoints and this interior critical point and determine at which point I have a maximum value. Okay, so evaluating at 0 is easy. I know that value. F of 0 is 5. And now I need to compute f of square root of pi and f of 3. And I just wrote square root of pi instead of 1.772. Either one will get you a correct answer here. What I need to do is use the relationship that my fundamental theorem of calculus gives me, which is, and I'll write it over here just so we remember. And in this situation, my initial condition is f of 0. I know f of 0, so I'm going to put in f of 0, which is 5, plus the integral from 0 to whatever the input value is of my derivative. So for square root of pi and 3, the value of f at those points will look like this. And after comparing, I noticed that f evaluated at square root of pi, or at 1.772, is going to be greater than f evaluated at 3. 5.578 is less than 5.679. And my explanation, I need to justify, first off, why I only needed to test this point and the endpoints. So since f prime changes from positive to negative only at 1.772, we need only consider that point and the endpoints as shown. So I've shown my work beautifully here. Thus, f has an absolute maximum at x equals 1.772, or square root of pi. All right, so for part C, I want to write an equation for the line tangent to the graph of f at x equals 2. Now notice this is the graph of f prime, but it still gives me some nice information, which is that at 2, f prime is less than 0. So at least I know that piece to make sure that I'm on the right track. Just a reminder, to find the tangent to a function f at some point x equals a, remember that means that that line intersects at that point when x equals a and has the same slope as the function f. So using point slope form, I simply have y minus the y value of f at that point equals f prime at that x value a, the slope at that point, times x minus a, the x value of that point. So in order to write this equation, I need to find f of 2, the y value when x is 2 of my function f, and I need the slope of my function at 2, f prime of 2. So based on what we did previously, we should have a good grasp on how to find f of 2 using the initial condition, f of 0, and then the definite integral in order to get all the way to 2. So I've written that here. This is the value of f of 2. And then f prime of 2 is pretty easy to evaluate. I'm simply going to evaluate my function f prime at 2. And doing so gives me negative 0.459. And that's what I expected. I expected a negative value between 0 and negative 1, and that's what I got. So now I can simply use point slope form to write the equation for my tangent line. My y value at that point is 5.632. The x value, of course, is 2, and this is my slope. So my equation will be y minus 5.632 equals negative 0.459 times x minus 2. All right, I'm going to now put up three former AP free response questions for you to work through. I will post the solutions and the scoring guide later on, but for now you should copy them down, spend 15 minutes on the problem, see where you get, finish it out no matter how long it takes, and do so for each problem. Really make sure that you're learning something from each, going back and reviewing any of the concepts that you might have forgotten.